Grazie Francesca, grazie. So this is because Fabrizio Caselli wants to be here and he cannot be here. So he will see it on YouTube. And then last year we had the whole seminar going on YouTube. It was algebraic groups. So it is fun to see afterwards what I've said. It's kind of interesting. No, the disappointing thing is it's going on YouTube because it's really visible to everyone. At least, it's okay. So we're talking about a subject, cluster algebras, which I don't know. And we're following this book by, I forget, Shapiro. I don't have it here. What's the name? It's Getman, Shapiro, and Weinstein. Okay. Being on YouTube, I cannot say what I think about this book.
There are many other possible choices.
But we started with this one. I already... No, this was proposed by Caselli, and I must say that now he has to read it because he proposed it. So, but the truth is that for today and tomorrow, next week, and what Marta does, we don't see cluster algebras at all, right? In your lectures, no cluster algebras? No. Okay. So it's really, what I do now is Poisson geometry, and I do a bit of simple groups and stuff like this. So this is preliminary. So let us do this. So we want to understand...
How many lectures are you going to give?
Me? I don't know. For sure...
At least?
2.
Because usually she starts but she never ends, so...
No, but it's like this, until the public is there and the clapping,
okay.
I
Go on.
I go on. It's,
so what you want?
The show must go on.
Just give up?
No. The thing is the following. There's 2 possible choices with a book like this one, which is I tell you what he says and it lasts very little. In 2 lectures I'm finished and then Marta speaks and we go. Or I tell you something more than what he says, because what he says really is like is a very terse and concise account of a very vast theory. And I decided to go with the second because I don't like to tell a story without knowing the characters. So today we're going to talk about the Poisson groups, which is something that me and Nicoletta should know well, right? Do we? Very well. I'm glad, because so when I make a mistake you'll be ready. You know Poisson groups. But I guess that you don't know them, and it's something that is worth... So this is the aim of today, to understand what is a Poisson group. Is there someone tall that puts this for me? Marco? It's really annoying, this little thing. Thank you very much. Okay, so what is a Poisson algebra? So we start with this concept. So if you consider, he calls it F. So this is a commutative algebra. Together with a Poisson bracket. Now, what is a Poisson bracket? It has all the properties of a bracket. Of a Lie bracket, sorry. So, of course, it's linear because this commutative algebra is over some field, say the real field or the complex field. So it'll be linear with that. But it will have the antisymmetric property. it will satisfy the Jacobi identity. I'll rewrite them because maybe not everyone is so happy with these properties. And then it has this, it behaves like a derivation. So if you do f and you put some bracket with g times h, this will be, what does it do? It does it with the first one. Let me see. Yeah, it does it. It likes to do it with the, it's the same because it has the symmetric property, so it doesn't matter. So it will be f gh plus g fh. So this, it behaves like a derivation. Now notice that it will be the same to have it on the second one because of this property. So you sort of can reconstruct that. Okay. What is an example of this object? So it's the most relevant example. So we do. Let us consider R2, but this is not our f. Our f is the C-infinity functions on R2. And we have to give this bracket, so the bracket of two functions. So this is the f, dx, dg, dy minus df, dy, dg, dx, by definition. Okay, you can see that it has certainly this first property, is obvious, this, and also the derivation property, this is Leibniz property, is clear too, the third one, because it's a derivation. So if you have a product. Now the only thing to check is the Jacobi, but if you check it, it's really straightforward. So this is a really direct check. So it's a direct check that is. And with the same effort, you can do R to N. So you can, it's the same thing. You do summation and then you have, so what is it? Right. So you have coordinate x1, xn, y1, yn, and then you have df, dxi, dg, dyj. Right, am I doing it right? Yes, you do all the possibilities. So it's the same overall ing. And again, this is a Poisson bracket. Okay. Then, whenever we have, so another definition which becomes important later, all the examples I provided, it doesn't do any example, I'm just telling you. In the book there are no examples. No.
I mean, the first example is just the determinant of the Jacobian of the map given by f comma g from R2 to R2. That's what the first one is, right?
Right. Yes, but if you wait just a second, I will tell you what is the most general that you can give on R to N and also on any manifold. Okay. So let me. We need some more. So this is something we will use later. So C in F is called the Casimir element. If it does the following, if FC is 0 for all F. So it's the central element for the bracket. It commutes with all. Okay, so this is Casimir element. For the moment, we just leave it aside. I just wanted to introduce it now. Now, coming to Stephen's remark, I want to. Okay, so So this, okay, well, I forgot to say this, of course. I'm taking my f is the C infinity on R to n, right? So the most relevant example for us of Poisson algebra is the C infinity functions on some differentiable manifold. So I'm saying that M is a Poisson manifold if C infinity M is a Poisson algebra. So we want to see how we can put these brackets on that, right? And so what does amount? So I think the Stevens remark was in this direction. What does it amount to put a Poisson bracket on a C infinity M? This was the direction of your remark, I think.
Yeah, I mean, I just happened to.
No, yeah, I know, but like this is very easy,
Sure,
right? These are two. We could have guessed it, right? Me and you together sitting with. But what does it take for a generic M to have a Poisson structure, to be a Poisson manifold? That's the question. So there is a definite answer. There is actually there are lots of answers on this. But the first easy remark is the following. So let's write it as an observation. So a Poisson, so M is a Poisson manifold. M is a Poisson manifold if and only if we have what is called a Poisson by vector, which I call pi, so that we can define for now I write it like that, okay? What he writes, then I try to make sense out of what he writes. Pi sits into the P to M, okay? With the further condition, let's write everything here, okay? Such that the bracket of pi with itself is 0. He writes like this. Now let's make sense, let's give it a meaning to what he writes so casually, because this is an interesting problem.
So what is the definition of a Poisson vector?
Yes, so it's a good question. So a Poisson vector pi is an element of the T to M, the tangent bundle. So it is the P. So it's the. So it looks like x tensor product y, where x and y are vector fields. With the further property that this Schouten bracket is 0. I explain what is the Schouten bracket.
So this is the definition of a Poisson vector, an element in T to M such that the
Schouten bracket
is it.
But actually the Poisson by vector, see, you could define it also saying, okay, I have a Poisson manifold, the Poisson by vector is exactly this pi that does this.
Yeah, yes, but since we have to understand what a Poisson manifold is.
No, I'm saying it. No, it's, I'm sorry, it's, this I know and I cannot, there is a decent eraser here. This one is kind of very stupid. Okay, we do with what we have. No, there is one. So if f if M is a Poisson manifold on C infinity M, we have the Poisson bracket. We have this thing, right? So we define this, we say we define pi such that when you do FG, okay, this you have, right? Then you have df wedge dg, and you do the pairing with pi. So this belongs to they both belong to T2M, right? So this is in T2M star, and this is in T2M, and you do the pairing, okay? So this makes sense. No, wait. So if you have this object, then this pi is defined, okay? Let's look at the example that we have, so to see what this pi looks like. For example, so I'm saying, suppose I already have a Poisson manifold. We have a Poisson bivector. And this...
and then you should prove that the Schouten bracket is...
Yes, I will do this. I will do. So let's look at the example of C infinity of R2.
Can you repeat again, please?
No, let me do the example, then I repeat everything, okay? So, in this example, I claim that pi is ddx, so this is the bivector. So, what is df wedge dg? It's a matter of notation after all, okay? So, it means that you are applying, you're doing the pairing of this. So you're doing, so this is, so this is like, this is what this is, right? So you're, I don't know, you can see this in different fashion, this pairing. It's a matter of, what I'm trying to say is that this thing means what I'm writing, that's all. So what is your question, Marta?
I don't understand. So there before that you have, and you are claiming that the other thing you have, and you are claiming that such a pi always exists.
No, I'm saying
Yes,
no.
she's proving one implication.
Yes, so, okay, let me tell you what the friends do. The friends say this, and this is the law. This is all they say. They say the Schouten bracket. No, they even say Schouten bracket.
And she's claiming that if I is a Poisson manifold, then there exists.
No, because I want to be
And
clear
then
on
pi in T2M such that, and
Okay.
she finds
No, I
pi
want to-
in that way. Then
Okay.
she has to prove that the Schouten is a Schouten or Schouten.
No, I want Schouten bracket.
Schouten.
Yes, I know Schouten. That I know. I want to see what it says, because no, he's very happy. He doesn't even say Schouten bracket. He says there is. It's me saying Schouten bracket because I know differently than what he says. So the reason I wanted to be pedantic about this is that he says, well, if you have a Poisson manifold, you have a Poisson bivector, which is something that looks like this. So you define it through this equation. You are not happy with this.
I know. To me, it's something I'm not familiar with. So I know I will not understand, and so.
No, but Marta, there is nothing. I don't want to. What is that to understand?
Perhaps you can define the Schouten bracket.
No, it's just no, because this is kind of destabilizing.
So let's see. If I don't know what has been
No,
of course
forget about shout and bracket, because why do I have to suffer? No, let's forget, because this is, let's look at just this implication. Forget about bracket or anything. If I have a Poisson manifold, then I have a Poisson vector. Period. Are we happy with this? No bracket, nothing. Because the bracket comes in to characterize those bivectors that are coming from Poisson structures. Okay? So it's one way is trivial, it's the other which is complicated. You understand this?
Don't look at me.
I know, but you are...
No, it's like this, really, Rita. No, because I would stop you every second and I...
But you have to. You have the next speaker. I will stop you every second.
You will stop.
I promise.
I will give up. I know that. If necessary, I will give up, Rita. Cioè, no, in my stuff you will stop me, but here I realize I don't have the background. So I cannot say, well...
I don't want to impose knowledge if you don't want. But I'm saying that really stop me because you'll be the next speaker.
Well, what I will do will not be about this.
Ah, okay.
So this is something which says if it were like this, I would have said I'm not going to do that.
No, in fact, I'm very surprised that we're in this session because this is very tough. It's going to be very, very tough.
Sorry, but we should prove this implication. It's obvious that such P that do this work exists or not.
Is this one? This is the definition. So pi is the element of the tangent bundle doing this.
Okay.
If I have this, then pi always exists, no matter what. This is the definition, this is the pairing, because this is in the dual and this is in the tangent bundle. Dual bundle, tangent bundle, there's a pairing.
But then we say that if Poisson manifold, then we have P exists, and it's obvious that it exists.
Yes, what I'm saying is that...
Because you use the pairing.
I use the pairing, yes. What upset me about the description of this by him, by them, is that they seem to assume that, well, you know, you have a Poisson manifold, you have a Poisson bivector, but like, what characterizes Poisson bivectors among all the possible bivectors? Not all of them will work. I'm saying, you know, if you
because you have some, because the Poisson bracket satisfies
exactly,
properties.
essentially, okay,
If you give such a
yes.
definition, then you have to prove that
okay,
is the Poisson
if
bracket.
you give this
So-
definition, it's clear that you have the skew symmetry property and you have the derivation property. What you miss is the Jacobian, and the Jacobian will be encoded in the Schouten bracket. So this is the extra property of that. So I even done a small calculation. So I tell you what is the Schouten bracket. It won't be very illuminated, this thing. I wrote it down. Maybe we shouldn't do all my calculation. So it works like this. So the Schouten bracket so is between elements of the is a generalization. So on the vector fields we have the Lie bracket, right? That's for sure. We can take the Lie brackets of vector fields. What is it is really what you think. It's it is x yf minus y xf. You apply your vector field to f, you get the function, you apply x to it, and this is the usual, right? The Schouten bracket, but we have a bivector here. So the bracket is not defined, but Schouten has defined a generalization of it. So if you have a product, so we have only two of them, but suppose you have a product that is a general thing. So this is so This is the definition of the Schouten bracket. And so I...
Point means
Eh?
tensor.
The dots are the tensor, the roll tensor. So I've made a small calculation for the case of R to n, because see, that's really, one says, oh, why do you care about R to n, right?
Rita, you take two elements in T2n. As a result, you get what?
Yes, I will do.
No, you get what? Where does it lie?
So if you take the Schouten bracket, so it will go one down, right? So it is. So this should be. No. So this is. So the Schouten bracket is on the tensor on
So
the.
you are defining it. You are defining the Schouten bracket between an element in T tensor and M. Can you write it down?
Yes. It's, this is Tm, say tensor M, and this is Tm tensor M, right?
Okay.
And what you
And you get
obtain is in Tm tensor, so it is M plus M and
Minus 1.
yeah.
Fine.
This is right?
Yes, that's right.
No, so what I was trying to say is that I've made this little calculation for the case of R to n, because I think it's instructive, this calculation, to see what is the condition that the generic pi must satisfy to be a bivector for this. And the thing, okay, so I may not do the calculation because we lose time, but I just wanted to get the feeling of what you have to do. So, the question, this is really a side remark, I don't want to spend time because, so suppose we have R to n, we are in this condition, and we wanted to define this, Fg is df dg, and then you have pi. For a generic pi, which looks like something like this, Pijx, so I'm using all the coordinates together now. So I'm not doing minus, I'm just, and I am assuming that pi ij is minus pi ji, so that I don't have to write minus.
Without F and G, yes? You're just taking
yes,
pi?
yes. Like this, okay? And the question is that what is this pi has to satisfy? And okay, it's
There are no p's.
yes, I put all together, right? It's
X, I, X, which means, I guess.
yes,
I guess.
this is
Functions, you have vector fields, so
yes, it's
the coefficients are functions in
we
X, Y,
very general,
in all the indeterminate.
right?
No, the coordinates in 2n are x1, x.
Yes, x to n. Yes, very, no, because it is like let's forget about what we did before. There was a special example. Let's look at general. So I want the Poisson structure on
Right, and he's just asking about the notation you are using. So
yes,
you are in R to n?
I am in R to n. I think I am. Am I?
That's what you wrote.
Maybe no. Maybe I'm in Rn. That's all. Yes, I don't need the 2. Thank you.
Are you sure about that?
I'm confused now. I took this example from Charlie Presley. I can go and look.
I mean, the standard Poisson bracket,
I know.
you need a symplectic
No. In the standard, yes, but that's not the standard.
You're not making
No,
example.
no, it's not the standard. I'm saying we've seen the standard,
No,
which is kind of
I
tricky.
thought you wanted to give us pi in that
No,
example.
no, because in that example, pi is like this one. It has constant coefficients,
Right.
and when you do the Schouten, it is 0.
So you are trying
it's-
to make another example.
I'm making, okay, I said it wrong. So I'm saying, the pi that we've seen before satisfy trivially satisfy the Schouten bracket, because the coefficients are constant. You cannot assume this in general, like you're because here there is nothing. This could depend on the point, right?
Of course.
Yes, and so I'm saying, okay, let's look at the generic Poisson structure on the Rn and see what are the conditions if you impose the Jacobi identity. That is my question, okay? Now, if you impose it, you see this, well, I don't want to do it because it's really taking us away. And so it is, you get something like this. Everything depends on the point, I'm not writing it.
So you're taking a general pi as you wrote
Yes,
it down.
and then
You define f, the Poisson bracket between f and you define a bracket fg in that
like
way,
this,
and then
you impose the Jacobi.
satisfies the Jacobi.
And if you do the calculation, which is really trivial, but you have to work the indices, that's all.
Okay.
You get something like this. So I write a dj to mean derivation with respect to the j coordinate. Summation on all of the indices equals 0. So this I look in Charlie Presley. Charlie Presley says that this is really the Schouten bracket. I'm not sure because I could not really. It looks similar to. If you try to do the Schouten bracket on this, I am not sure about this calculation. But Charlie Presley are very casual because they define this as the Schouten bracket. This is the Schouten bracket of a bivector, and this is the condition. Because they only care about bivectors, that's the truth. Yeah, but I don't really want to take us far. I'm just telling you that there is not. So there is an if or no if there is this further condition. That's all. It's very reasonable. There must be some extra condition on that.
So this is the condition that any Poisson bivector on Rn must satisfy if only if
Right.
So you're
So
just writing that.
Huh?
You're just writing that.
No, but if you write the bracket and you impose Jacobi, it will come out. It's an exercise. I've done it.
Yeah, you have.
That is simple.
Yes.
Okay, it's not at all difficult. Now, then it could be, I just want to spend 1 minute because I've done some research on this, so I feel it could be what are all the possible Poisson structures on a manifold.
Sorry, Rita, I guess the sum is over j.
The sum is over what? Let's see. I've done the calculation, so I must know the sum. So the sum is over everything, isn't it? So there are these indices. I don't know, I'm summing.
Right.
So,
I have to be.
okay, so there could be this question, if you have a manifold, how do you know there is a bivector, or if you prefer a Poisson structure, whatever of the two, right? Actually, it's better. What the guy is saying is that the bivector is more accessible because it's one element of the tangent bundle, you know, the tensor product. So it's more accessible object than just a bracket. That's the. So, what are all the possible of them, right? It's a good question. This question was completely answered by Onsevich in his work on, you remember this Poisson deformation quantization and Poisson manifolds. he produced all of them and classified all of them. He got the Fields Medal like the year after, not just for this, but for while people were trying to construct the Poisson structures, he not only constructed but classified all of them with explicit formulas through Feynman diagrams. I tried to read the paper. Have you tried it? No.
I listened to Concierge talk, some Concierge talks, but I did not understand any words.
The paper is so Marianne and I wrote like a considerable amount of work for half a page. To clarify half a page of Concierge work, we worked it out and said, you know, we think we know what it means in this half page, and we wrote a paper first.
Was it the
First one.
page?
No, it's a page in the middle. In the middle, it makes an example. It says, oh, conjoined orbits, you know, my method applies, blah, blah, blah. And so we're like, we think we understand what it means. It's very interesting. Okay, so I was disturbed by the fact he did not make any comment about this, and so I wanted to say more. But we don't really need this, so we're happy. There is some.
Sorry,
yes.
one question. So that means that unlike symplectic geometry, there is no canonical local form for Poisson.
There is no. But if you wait, you have to be patient because the story is just at the beginning. I have to tell more. So it. Okay, so I need one more thing. So assume that now M is a Poisson manifold. So we know what that means. And then we want to define what is the Hamiltonian vector field associated with function. So if we take F, so we call VF the Hamiltonian vector field associated with what is this thing? It's defined like this. So it is a vector field, so it acts on functions. So F and G, also G is in the C infinity of the manifold. And so this is we define it like this, okay? Now, he makes the following observation, that when you have a vector field and you apply it to a function, the result that you get...
So it is add F.
Definition.
It is add F.
The adjoint F.
Right.
Yes, thinking about F for this, yes. Now, I wanted to make a remark which is important, that, you know, if you have a vector field acting on some G, you see that you can view it as the pairing, right? So you take the differential and you look at this pairing. So this is the Poisson bracket. So it tells you that the bracket depends only on the differential on this. So if you add a constant to your function, the bracket will not fill it, essentially. This is a remark that is interesting. So,
Well, it is a derivation.
Is a derivation? Yes, is another way of saying it's an observation. Now, this association of a vector field to function, see, so we can push this picture more. So we can define a so we see that to a function we can associate a vector field. So to the differential of the function we can associate the vector field. So what this does is to create a pairing between the cotangent bundle and the tangent bundle. So it's okay. I'm just saying things which are sort of trivial. Is the language that is complicated. When the pairing, when you have an isomorphism, then it is said to be symplectic, the manifold, and there is no Casimir. Because the Casimir are those that sort of make the bracket degenerate. The Casimir are those elements that are zero ever, right? So this becomes, if this, what does he call this? What?
Is it necessary and sufficient? Are you claiming that if,
No, it's a definition. It's a definition now. I'm saying, if this thing, if this map is an isomorphism, we say that M is symplectic. But wait, now I'm coming. So, if this...
if the bracket is not...
Wait a moment, this is iso, then M is called the symplectic. What happens here? Because one may know what is a symplectic manifold. What happens here is that to Poisson bivector there will be a corresponding to form. So there will be, so to pi, the bivector will correspond omega to 2 form. In this, no, sorry, it's the 2 tensor, this is, okay, there will be 2 form. And this will be the symplectic form. And the fact that it's non-degenerate should come out from the absence of Casimirs, right? It should be the same. Like the Poisson. Now I'm a bit confused. How you write? Well, in coordinates it's very simple. You just write this in coordinates.
It's the same as the radical of the form.
The radicals, yes, it's not
So
the
the radical in zero form is non-degenerate. And the symplectic form
is non-degenerate, yes.
Antisymmetric, non-degenerate.
right. No, but I'm thinking how to write a Poisson bracket directly from the symplectic. I think that you have to go to coordinates through that isomorphism. This you have to go. Right. Okay. Now he says other beautiful things. We totally no whatsoever worry. He says, what happens if we don't have a symplectic? Suppose that. So I'm just telling you because what is leaving out is too much. So he says that if M is a Poisson manifold, which is not symplectic, so